Number 5, relative versus absolute dating. There are two big principles in dating, and we're going to have a look at these two big principles, and you need to know a little about both. So let's imagine you are in front of a layout of sedimentary rocks, and you are asked to say, well, can you say which one's older, which one's younger, what's the age? So you could have two approaches to this. The first one is you could simply have a relative dating approach and say that, well, we know that sedimentary rocks pile up, so the ones towards the bottom are older and the ones towards the top are younger. So you're simply saying that the more you go towards the top, the younger the sedimentary rocks are. Or with other techniques, you could be very precise and actually give an age using specific methods for certain layers. So you could, for example, say, well, study and say that this layer here is 120 million years old. The 5 here is the inaccuracy, and the one towards the bottom is 140 million years old. So with both methods, you get the same results, that the ones towards the bottom are younger and the ones towards the top are, the ones towards the bottom are older and the ones towards the top are younger. However, the second technique, absolute dating, is more precise, more specific, because you've got an indication of ages, precise ages. 5.1, principle of relative dating. There are two things you need to know. The first one is that it simply determines if objects or events are younger or older. And the second one, it's qualitative. You're not going to give specific dates when you use this type of dating. Task. State in which order the different geological events took place. So we're going to do an example to understand how to use relative dating. This is maybe just slightly borderline with your syllabus, but just to give you an example in what people would study in geology, for example. Well then, let's date the events. So first thing, you know that sedimentary rocks pile up, so the first event will be the formation of this sedimentary rock here. Then more sediments would deposit, solidify. We would have the second event, which is the second sedimentary layer. Then the third event would be the formation of the third sedimentary layer. Now then, we need to look at something that affects all these layers. Number 4 will be the injected magma, because it goes through all of the layers. So therefore it must have happened after the layers were deposited. And the last thing is the field crack. You can see that the field crack will affect all of the events, even the injected magma. So that means this is the last event. If the field crack had happened before the injection of magma, well, you wouldn't have this crack here in the magma. So that's why we can prove that it's number 5. There are two main techniques in relative dating that you need to know. The first one is stratigraphy. Basically, it's what we've been saying for a long time now, is that layers will deposit the first one at the bottom, then the second one on top, then on top, then on top. And when you add layers, they are younger. And the second one is cross-dating. When you use certain fossils, when you compare them, you see which fossils are in which layers. You can also date which layers were before and which layers were after. 5.2, principle of absolute dating, general knowledge. the few things you need to know. It determines the age using radiometric techniques. We will detail one of these radiometric techniques, the one which uses carbon-14. It's an absolute dating and it's quantitative. That means we're going to give a precise date, a precise age to the objects. So exact age of the remains, and it's more specific than relative dating. 5.22 carbon-14 dating method. You really need to know this. You probably remember when we did Rubin and Kammen's experiment that there are two types of carbons, carbon-12, which is the most abundant one, and carbon-14. Well, there's another thing you need to know about carbon-14 is that it can naturally decay in a radioactive reaction, which plays out as follows. This is carbon-14 here. Oops. This is carbon-14 here. And in this beta reaction, it will disintegrate into a nitrogen-14, and it will also produce an antineutrino and an electron. This is interesting because that means that in a sample which has a certain amount of carbon-14s, well, as time goes on, there'll be less and less carbon-14s and more nitrogen-14s. Let's have a look in a bit more detail with another diagram. Statistically, the decay of carbon-14 will show a graph like this. What's interesting is that scientists know that if half the amount of carbon-14s disappears, is reduced, then that means that it took one half-life, and that is equivalent to 5,730 years. If a sample only has a fourth of the initial amount, so here we have, imagine the sample started with 10 grams and now there's only 2.50 grams. Well, we know that it takes another half-life, so more than 11,000 years to decay. So what scientists do, they take a sample and they compare the percentage of carbon-14 compared to a modern object or the atmosphere to know, in a sense, how much the object has lost, if we may say so, their carbon-14s, how many carbon-14s have decayed. And basically, when you know the percentage of carbon-14 that decayed, you can then know how old the object is. The best way to check you've understood how this absolute dating method works is to go through this back exercise that you will find in your booklet. So, back exercise on dating mammoth fossils, and it was from 2014. This is the end of the video. See you next time. Bye.
I am a plant, a living thing, making food for us, photosynthesis. I'm taking in carbon-14. I'm a dinosaur, a living thing. I'm eating plants, the plants are green. I'm taking in carbon-14. What was that? An asteroid? And I ain't got